All right, AP Chemistry students, welcome to Chapter 9. I'm just going to walk you through some of the highlights here in Chapter 9 and just mention a few things so that it serves as both an introduction, but also if you want to come back to this after you've read the chapter, it'll serve as kind of a review and a refresher as far as what you need to focus on for the Chapter 9 test. Chapter 9 is going to continue its discussion, the discussion about bonding, and we're going to just pick up kind of where you left off in Chapter 8 and continue to talk about bonding and focusing on those orbitals. And we're going to be talking about different types of orbitals, two models specifically, two models that look at how do we get the electron regions, those orbitals, in a molecule that came from the electron regions of separate atoms. So we're going to be looking at two different models, the localized electron model and the delocalized or the molecular orbital model. Okay? All right, let me just give you a quick example here as we look at one particular molecule. So we're looking at a molecule of methane. So imagine you've got a separate carbon atom, and that carbon atom has s orbitals, it has 3 p orbitals, as you know, if we're talking about the outermost orbital regions. Okay, so we've got s orbitals, we've got 3 p orbitals, and we would have electrons in those different regions, or the potential of electrons in those 4 different regions. Okay, this would be a carbon atom by itself. But now that carbon atom comes into the possibility of bonding with 4 hydrogen atoms. Each of those hydrogen atoms have electrons as well, and they are going to share electrons with the carbon and make a molecule. Well, these original electron regions for the carbon, your s and your 3p, those are where the electrons are or could be for the carbon. But when that carbon bonds with 4 hydrogens, those regions no longer exist because now the regions are in between the carbon and the hydrogen atoms. So it's not going to look like it did originally. You're not going to have an S region and 3p regions anymore as you did in the original carbon. You're going to have 4 identical regions around that central carbon atom. So what the theory is, or the model is that these 4 regions here for the central carbon atom are going to hybridize. In other words, those regions now are going to merge together. They're going to morph together and make 4 equal electron regions where the shared electrons can now be housed. Those 4 regions come from 4 atomic orbitals. So you're going to get 4 molecular orbitals. These are all going to be identical. 1, 2, 3, 4 around that central atom, coming from, the theory is, the model is, 4 different atomic orbitals of that original carbon atom. These 4 molecular atoms, or molecular orbitals, came from the s and 3 p's, and therefore it is going to be called sp3. Each of these orbitals, there's one sp3, there's another sp3, there's another sp3, and there's another sp3. You're going to have 4 sp3s coming from 1, 2, 3, 4 different atomic orbitals. Okay? And then the theory continues from there that, okay, what if you don't need 4 electron regions around the central atom? You only need 3. So in this case, around this carbon, let's say, you only need 1, 2, 3 regions. So you're going to have an S and 2 P's from this carbon hybridizing, morphing into 3 regions around around this carbon atom, and each of those regions would be called an sp2. Don't worry about the double bond right now, okay? What if you only need 2 regions? Well, if you have 2 regions, then this carbon atom here has 2 regions around which there are electrons. Then the s orbital of the original carbon and one of the p orbitals of the original carbon are going to hybridize, and they are going to form 2 sp orbitals, molecular orbitals. There's one sp, there's the other sp. Okay? So that's the idea of hybridization, that the electrons then are going to be localized in certain regions around the central atom. What about those double bonds? Well, those double bonds are formed because of the p orbitals that are not part of the hybridization. Those overlap. So here you've got a p orbital. It's actually, this whole thing here is a p orbital of the oxygen and the p orbital of this carbon. That's where the electrons that are in each of those p orbitals are going to be shared and overlap, and that's where you get the double bond. Part of the bond is from this bonding here that's happening, the sharing of electrons between the overlapping of those orbitals, and then the, which this would be a hybridized one. You've got sp2, sp2, sp2. You've got 3 sp2s there, and that's where one region is, and then this is the second region. I know there's 2 parts to it, but remember, p orbital has 2 lobes. The second part, this is not 3 bonds, it's actually 2. Here's one, head-on overlapping, that's called a sigma, and then the parallel overlapping here is called the pi bond, and that's the second bond. So that's where you get a double bond, okay? So you'll learn about that. You'll learn about sigma bonds. That's where orbitals overlap head-on, like this. And you'll learn about pi bonds. That's where overlapping happens because the orbitals are parallel to each other, okay? So the non-hybridized p orbitals are able to overlap and form that multiple bond, double or triple bond, okay? So that's the one model. The other model has to do with energy levels. So as you look at, I'll just mention here really quickly here, this is a nice little summary for you. How do you come up with the different hybridized models? Well, you have to draw the Lewis structure of your molecule. Then you determine how many different electron pairs there are using the Vesper model, and then you just match it up with the possible hybrid orbital selections. Okay, so it's just this easy. After you draw the Lewis structure, you figure out how many electron pairs there are, and then that is going to lead you to what kind of hybridization is involved. So this would be your central atom in here, and it has an sp and another sp. Here would be another atom on this side, another atom on this side, and it has 2 electron regions, okay? If it has 3 electron regions, and they're all in bonding, they're all bonding regions, then you're going to have that situation, that geometry, and it is sp2. And you just continue down this chart here for each of the different number of electron regions around the central atom. Okay? The other model deals with basically energy level. So to look at the other model, which is called the molecular orbital model, you're looking at different energy levels. So in every situation when you have a bond, let's look back up here for just a second, okay? Anytime here, I'll use this example right here. Anytime you've got a bond, electrons can be found in between here. They can be found in between the 2 atoms, and that's helping the bond, or they can be found outside of the bond. So these would be bonding, and these would be anti-bonding. They're not helping the bond at all. They're actually detracting from it. It doesn't mean that this molecule is not going to happen. It just means that which is going to win out the situation. Are you going to have electrons here that are causing the two atoms to bond, more than you're going to have electrons on the outside kind of detracting from the bond. So you're going to have bonding electrons and you're going to have anti-bonding electrons. The bonding electrons help the bonding and are usually at a lower energy position. The anti-bonding electrons, in order for them to be sustained, that's going to require more energy. So the next model here, the molecular orbital model, has to all do with energy. Either you're going to have bonding, which are going to help the bond form, or you're going to have anti-bonding, which is going to detract from the bonding. Okay? So if you've got a hydrogen atom and another hydrogen atom, and they come together to form H2, your molecule, you're going to have electrons, one electron, this arrow right here is representing one electron from this hydrogen, which was in the s orbital of that hydrogen, and you're going to have one electron, this arrow right here, from this atom of hydrogen, which was in its s orbital, and they're going to come together to form H2. Well, where are they going to reside? The order in which they reside is always going to be lowest energy first. So you're going to form a bonding. This is bonding, this is anti-bonding, and this is for the two s orbitals sharing their electrons. So you would first fill the molecular orbital, MO is molecular orbital, the bonding one first, and then you would fill the anti-bonding later. Okay, the lowest energy always gets filled first, and then you would move upward. Now this is simple because both these electrons are going to go into the bonding energy level, molecular orbital. You always put 2 electrons in each orbital, just like we did with the atomic orbitals. Okay. Here's another one that kind of spells it out here. Hydrogen atom number 1, hydrogen atom number 2. They're going to overlap. They're going to form a sigma, means they're overlapping, right? Head-on overlapping. And this is your sigma anti-bonding. These 2 electrons are going to drop into the bonding first, and the anti-bonding is going to be left empty, which means both these electrons basically are going to be found between the atoms. There aren't going to be any electrons out here in the outer regions of that molecule. Okay? In order to find the bond order, which tells you kind of how strong the bond is, it tells you a little bit about whether this bond is going to occur or not, you find what is called the bond order. Let's look at this situation. Let's say you have, this is the molecule H2 negative. So it actually has a charge on it, which means it has 3 electrons. This hydrogen atom has 2 electrons, so it's charged. This one only has the 1, so it's neutral. So now we're going to fill them in. So you've got 3 total electrons. You're going to take 1 and 1, drop it in the lowest MO first, molecular orbital, and then that third one has to fill in the anti-one. So you're going to have, in this situation, you're going to have 2 that are helping the bond. You're going to have 1 out here somewhere in the outside regions, in the anti-bonding region, you're going to have another electron. This anti-bonding region is kind of detracting from the bonding situation. It still might be held together. This still might form a molecule, but it's going to be possibly a weaker bond as a result. How would you determine that? You look at the bond order. The bond order basically is you take the number of bonding electrons, that would be 2, subtract the number of anti-bonding electrons, that would be 1, and divide by 2, and you get an order of 1/2. The larger the bond order means the greater the bond strength. Okay? So it's that simple. Of course, they can get a little more complex, but here we got lithium and lithium coming together, 2 lithium atoms forming Li2. Again, you can see this is the 2s, this is the 2s, but you're going to have 2 electrons in the sigma 2s bonding and none in the anti-bonding. Okay? Here you got boron and boron, and you would have to figure out how many electrons are going to fill these different molecular orbitals. Now in this case, boron has more than just 2 valence electrons. So now the order is, you got to look at the order here. First you're going to have a sigma, and then pi, 2 pi, and then you have anti-pi and anti-sigma. So you'll read about this and figure out the order, and you just fill them in increasing energy level, and then you'll be able to figure out which of these molecular orbitals get filled. Notice, in most cases, the bonding ones get filled first, and then the anti-bonding get filled second. Okay? You do need to know about paramagnetism, so make sure you read about that and understand what that means. And its counterpart then is the dimagnetism. So make sure you understand those 2 terms and when something is paramagnetic and when is diamagnetic. All right. This is just showing you the order of these different bonding and anti-bonding. You don't necessarily need to know this order, all right? But it's just showing you that for some molecules, the order of these bonding and anti-bonding molecular orbitals may be one way, and for other molecules it may be slightly different. Okay, but you can see they're getting filled. In whatever order they are, you fill the lowest energy first and then move up to the highest energy. And you may see, just by looking at this chart, you may be able to determine when something is paramagnetic, when it is diamagnetic, when it is diamagnetic, when is it paramagnetic, when is it diamagnetic. Okay? And you can see here they calculated the bond order. I bet you can see if you can calculate the bond order using the bonding electrons minus the anti-bonding electrons divided by 2. Okay? I would encourage you in all chapters to look at the example problems. So look at the example problems, follow them, read through them. There's good example problems there that you should definitely look at. Okay? In 9.4, they're again continuing the concept of molecular orbitals, but they're doing it with heteronuclear diatomic molecules. In other words, 2 atoms that are not the same, like nitrogen with some other atom like oxygen. But the concept is the same. You're going to fill up the bonding and anti-bonding molecular orbitals from lowest energy to highest energy. Okay? Here's an example for you to look at. All right, basically, that is what you need to know. You don't need to worry too much about 9.5. I encourage you to look through it. But basically, it's just saying that the localized electron model, which is using the hybridized orbitals, and the molecular orbital model, which is using the energy levels, they all have their deficiencies. They have their weaknesses and strengths. If you combine the 2, then you kind of bring in the strengths of both of them and negate the weaknesses of both of them. Okay? But that's not really a big deal for you to focus on. All right? I would encourage you to look at the review section here. This review section is very helpful. Gives you all the terms that you need to know, as well as summarizes exactly what I just talked about here in Chapter 9. Okay? As always, if you've got questions, don't hesitate to let me know. And I hope this is helpful as you kind of know what to focus on and kind of know what to spend your time studying. Okay? Keep up the great work.